Hi, welcome to Gas Law Test Review. Gas laws is a application of what we learned in chapters 10, 11, and 12. It's the first application of something mathematical since we began. Gas laws is difficult in a sense because it's not chemistry. It's actually physics. And why do we study it? Well, we study in this course chemical reactions. And we study chemical reactions in environments that are affected by things like pressure, temperature, etc., and volume, a space in which to occur. So it's important to understand how these conditions affect chemical reactions. Now, when you have an explosion, it's the production of gases. That's what an explosion is. An explosion is an absolute and utter production of gases at incredibly fast pace, in which the gases are produced and pressure changes occur. Now, when these pressure changes occur rapidly, we get that clap, that bang, that explosion. If I put my hands together, if I put them together slowly, you can't hear it. But if I put them together quickly, I am trapping the gas in my hands. You can hear it. I'm kind of cupping my left palm and hitting it with my right fingers, and my fingers are as closed as I can get them, and I'm going to clap. Now what I'll do is I'll open my left palm so it's completely open and very little chance for gases to be trapped, and I'm going to hit it with the tips of my right hand. You can see how it's not nearly as loud because I'm not trapping as much gas underneath my fingers. But if I curl up my left palm ever so slightly, I can trap those gases, and I can change the pressure rapidly. And when that pressure changes rapid, you get that clap, that sound wave, that explosion, that mechanical wave. Sound is a mechanical wave. So the study of gases and chemical reactions are going to be very important. Think of an airbag in a car. How that whole concept that has saved so many lives has to do with the production of gases, nitrogen specifically. So why did the canning industry use nitrogen when they canned food? Why would they use nitrogen? Why not use another gas like oxygen? It makes no sense unless you understand the concept of gas laws and chemical reactions. So gas laws essentially is another foundational plank, so to speak, where you need to know gas laws in order to understand how chemical reactions occur. We're not yet necessarily studying chemistry. We're studying one of the foundations of chemistry, and we need to know this in order to study chemistry. So let's review the test. Right away, you're going to see a matching, and you're going to see the gas laws. Boyle's law, Charles' law, Dalton's law, Graham's law, Gay-Lussac's law, and the ideal gas law. Okay. Another thing that's going to be very obvious in gas laws, the study of gas laws, are two mathematical relationships. A linear relationship and a nonlinear relationship. An inverse relationship, kind of like a hyperbola, where indirect, inversely proportionate. If you look at the first quadrant of a Cartesian coordinate system, and you start in the upper left, just to the right of the y-axis, and you go down, curve to the right as you're going down, and then as you get close to the x-axis, you're going to approach it but not intersect it. Okay, so it's going to look kind of like a parabola almost, right? But kind of opened up parabola, and that's called a hyperbola. And that's going to be the relationship between two variables, where the variables are a product such as x, y, and that equals a constant. Let's say 1, for instance. So as x is very high, y has to be very small, and vice versa. And we'll explain that in class, or if I haven't done so already. So an inversely indirect relationship is one in which x and y is a product. It's a product constant. X, y equals a constant. And then the other one is, and this may sound confusing, but the quotient of x and y is a constant. It's a little weird, isn't it? But y over x equals a constant. Y over x. Why y over x? Because we write equations in terms of x. So y equals mx plus b, for instance. Why did I say mx plus b? Well, let's say that b doesn't exist. Let's say that the function, the line, intersects the origin. So b is 0, so it drops away. Okay. So it's y equals mx. Well, m is a constant. It's the slope, right? So divide through by x, and you get y over x equals a constant. So y over x equals a constant. Solve for y equals mx. The equation mx, you know, is linear. So y equals mx. It's a linear function. So, in other words, when y goes up, x goes up. And let's test that. Y equals mx. So let's say m is 1. All right, let's say m is 1. So y over x equals 1. All right, so you get 5 over 5 equals 1. All right, good. So double y, 10. Well, what do you have to do to x to keep it equal to 1? Well, you got to double it because it's going to be 10 over 10. So as y goes up, x goes up. As opposed to xy equals 1, so 10 times 1/10 equals 1, 100 over 1 over 100 equals 1, etc. So as one goes up, the other goes down for an indirect, inversely proportionate relationship. And when one goes up, the other goes up, as in a direct, proportional quotient, y over x equals a constant. So when you have a relationship where you have a product constant, that's an indirect, inversely proportional. When you have a quotient constant, that's a direct relationship. All right, let's start with Boyle's law as a review of the gas laws. Right, I have a syringe, and it's a special syringe. There's no needle, but there is a place for the needle. So what I do is I prevent the material from being pushed out of the syringe. So it's a cylinder, isn't it, really, with a piston, the plunger. All right. Right. So instead of a medicine in there or something, I put just air. And I put the plunger in. So I have what do I have? I have a cylinder, a volume full of air, and I put the plunger in, and I press the plunger down. What happens? As I increase the pressure of that space, I'm going to decrease the volume of the air that's in the plunger. So increase pressure, decrease volume, right? So as I increase the pressure, I decrease the volume. Now as I let the pressure off, I'm going to increase the volume. All right. Now, let's say I'm not touching the plunger. It's a magic syringe. All right, I'm not touching it. But what I'm doing is I'm heating it. I'm putting it in an oven. And I'm heating the plunger and the cylinder and everything else. And it's a magic plunger. It's not going to melt. It's going to be fine. Okay. Well, the gas inside the plunger, inside the cylinder, is going to heat. So as the temperature of the gas, as I'm going to heat that, what's going to happen to the volume of the gas? Well, as I heat the gas, I increase the temperature of the gas. I'm going to increase the volume. Makes sense. As I decrease the temperature, I'm going to decrease the volume. You know this. This is no big deal. Gay-Lussac's law. Well, what does that say? Well, that says that as I increase the pressure, now really press hard, like with 10 million tons, right? What's going to happen to the pressure inside? I'm increasing the pressure, millions of tons. So what's going to happen to the temperature of that gas? Well, what's happening is I'm drawing the air molecules very close together, so the collision rate is greatly increased. So I'm going to increase the temperature of that gas because I'm moving the molecules closer together. Now, let me just say this. When I'm looking at pressure and volume, I've got to keep temperature constant because otherwise we get all fouled up with the volume changes. As I'm looking at volume and temperature, the pressure's constant. And when I'm looking at pressure and temperature, the volume's constant. So I've got to, understand that one's constant. So let's look at this. So let's say that they're all together. I'm pressing that volume, but the volume is decreasing with the increased pressure, and the temperature is increasing. And so what's the relationship among volume, temperature, and pressure? Well, let's see. Volume and temperature is a quotient. Pressure and volume is a product. Volume and temperature is a constant. Okay, that's a quotient. And pressure and temperature is a quotient. Okay, so the relationship would be PV over T. So the relationship among pressure, volume, and temperature would be PV, P times V divided by T. That's going to be the combined gas law. And then we have Graham's law, which I'll go into in a little bit. And that's about, let's see, that's about it. Oh, we have the ideal gas law, where we're not comparing a before and after view. Let me explain what that means just momentarily. If I have pressure and volume, let's say I have pressure times volume equals pressure times volume. That means that if I have a gas, all right, I have 22.4 liters of gas at 1 atmosphere of pressure. Okay? Right. I double the pressure. So I'm going to have 2 atmospheres of pressure. What's the new volume? So PV1, set 1, PV first conditions, is going to be 1 atmosphere, 100 kilopascals, however you want to word it, and I'll get into that in a minute. And I multiply that times the volume, I'm going to have that equal to the new set of conditions. They've got to be equal because there's a relationship. Well, what's the relationship? Remember that hyperbolic line I talked to you about? Well, any point on that hyperbolic line, there's going to be a set of conditions. Let's put a dot. Put an imaginary dot on that line, okay. Go over to the y-axis. All right. P. All right. Go down to the x-axis, V. If I multiply those two together, they're going to be a constant. If I go somewhere else on the line and come up with a P and a V, those two variables, P and V, they're going to equal a constant as well, and the constant's the same. Okay. So what does that mean? Well, what that means is that you can say PV first set of conditions equals PV second set of conditions. You know P1, V1, you know one of the other variables, so I said you double the pressure, so we know the P2, so calculate V2. So P times V, P1 times V1, divided by P2 equals V2, equal, easy. Okay, what else? Ideal gas laws, you're not looking at 2 sets of conditions. You're looking at this very ideally, and you're saying to yourself, right, PV equals nRT. PV equals nRT. So P times V equals the number of moles times the ideal gas constant times temperature. So if I know 4 of the 5, I can come up with the remaining one. So if I have a pressure of 1 atmosphere, a volume of 22.4, I have a known R, and I have a temperature of 273 Kelvin. Temperature always has to be Kelvin, always, because it's based on absolute zero, because P over T equals P over T. T can't be zero, so you can't have it Celsius. So it's got to be an absolute scale. I can come up with the number of moles. I can calculate the number of moles. And I know the number of moles, what it's going to be. Okay? It's going to be 1, but you should know that. All right. Why don't we look at some problems? Let's look at some problems. Okay. So the first thing is going to be some matching. You're going to have to know Boyle's law, Charles' law, Dalton's law, Graham's law, Gay-Lussac's law, ideal gas law. You're going to have to know, for instance, some more matching. Effusion, compressibility, diffusion, partial pressure. Remember Dalton. You're going to have to know why is it easier to compress a liquid or a solid. You're going to have to know what happens when you apply a pressure to a volume at a constant temperature. You're going to have to know what happens to that volume. You're going to have to know what would happen to the pressure if you kept the volume constant. How does a gas propellant move when an aerosol can is used? Okay, let's take a break. You'll never know I was gone. Now, if you had an aerosol can, and they don't really exist anymore, you really wouldn't really know them. But let's say you have a can, a spray can, and it's under high pressure, of course, and you hit the knob. So the aerosol can will go from a region of high pressure inside the can to a region of low pressure outside of the can. Well, if you had your finger near the tip of the nozzle where you had the interface of the drastic drop in pressure, what do you think the temperature would be at that point? Would it be greater than the can, which would be at room temperature, of course, or would it be less? Would it be high? Would it be room temperature? Would it be greater than room temperature, or would it be less than room temperature? What would the temperature be at the nozzle where the pressure is going from high pressure inside the can to low pressure outside the can? Now, if a balloon is squeezed, what happens to the pressure of the gas inside the balloon? What happens to the pressure of the gas inside the balloon? Now, you're going to have to understand the relationship with moles and gases. You know that 1 mole of any gas at STP, standard temperature and pressure, which is 273 Kelvin and 100 kilopascals, 101.3 kilopascals, same thing. But we rounded to 100 kilopascals. It's going to be 22.4 liters. That's the volume. The volume of 1 mole of gas at STP is 22.4 liters. So, let me read you a question. It says, if 4 moles of a gas are added to a container that already holds 1 mole of a gas, how will the pressure change inside the container? So, I'm keeping volume constant because it's saying you have a container, it already holds 1 mole of a gas, and I'm suggesting that gas, that 1 mole of gas is in a container, a rigid container, and I'm going to add 4 more moles of particles. How is the pressure going to change? How is the pressure going to change? If I keep the volume constant, how is the pressure going to change? Let's look at another problem. Why does air escape from a tire when the tire valve is open? Think of this. Think of diffusion. The flow of matter or energy from a region of high concentration to a region of low concentration. And as water will flow downstream, energy and matter will flow from a region of high concentration to a region of low concentration. So there's obviously more air on the outside, but it's very concentrated in the tire. So it's going to come out because the high pressure will force the air out. So it's going to move from high pressure, high concentration, to low pressure. So the pressure outside the tire is lower. That's why it's going to move. Okay. What happens when you do things like this? When you double, like if you double a temperature, or double a volume, what happens to the pressure? If your temperature is held constant, if you double the volume, what happens to the pressure? Okay, if your temperature is held constant. What is the ideal gas law? What is the equation for that? Let's see, what else? Shall I read you a question? If the atmospheric pressure on Mount Everest is 1/3 the atmospheric pressure at sea level, the partial pressure of oxygen on Everest is 1/6, 1/3, 1/2, or equal to the pressure at sea level. Remember Dalton's laws of partial pressure. Remember Dalton's laws of partial pressure. So you're going to have to, let's see, here's another one. Let me read you this one. If oxygen is removed from a sample of air as iron rusts, gas laws, chemical reaction. Remember, rusting is the combination of oxygen and iron. What happens to the partial pressure of oxygen in the air? If the oxygen is removed, what happens to that partial pressure? Does it increase, decrease, stay the same? What happens to it? So you're going to have to know the concept of volume, moles, temperature. Do you use 0 degrees Celsius, or what do you use really? You can't use 0. For instance, I think I said this before, because 0 can't be in a denominator. And if we're going to be using denominators or fractions, or dividing PV equals nRT, so PV equals nRT. So if you're going to solve for n, you've got to divide through by t. So t will be in the denominator, correct? So n would be PV over RT. So you can't have t in the denominator. So you can't have 0 degrees Celsius. So you need Kelvin. Yeah. You can't have the negative either. That would be a little weird. So you want to look at Graham's law. There's a relationship. Look at the mathematical relationship between molecular weight and velocity. Okay, look at the equation. I'll go over that in a few minutes as well, a little bit more thoroughly. I want to get through some of this other stuff. Let's see. What happens to the temperature if the volume is held constant and I increase pressure? What is Dalton's law of partial pressure? What does it say? What does it say specifically? And I think that's about it. I'll come back. I'm going to take a break. You'll never know I was gone, and I'll come back and we'll finish up. Let's talk a little bit about effusion and what effusion of gases are based on. Well, the lighter, like helium, the lightest gas is going to move more quickly than, say, oxygen. So the size of the molecule is important relative to this. Let me see if I can pull up the can't see it here. Let's see. Let's see if I can pull up the textbook on this. Because I just don't want. I want to read this to you. I don't think. Can't seem to find it here. I had it at one point, but I don't seem to have it any longer. Wait a second. Maybe it is under. I have no idea. Anyway, so look at the equation for the law of effusion. Look at the left side. It says the rates of the gases. Let's take two gases, A and B. All right. The rates of those gases, in other words, how fast they're moving, will be based on their size. Okay. So they're going to equal, right, that ratio of rates of movement, the rate of the gas, the rate of the flow through the little pinhole, through the little opening, let's say the little pore in the balloon. That's why one reason helium is such a bad gas to use in a balloon, because it can escape and the balloon will just spontaneously deflate and become smaller. You've seen this as a young person who likes, balloons, etc. Go and get a helium balloon at a fair. Well, the rates in which the gas escapes is going to be equal to the square root of the ratio of the molar masses, but in reverse, the reciprocal of that. So if it's going to be A over B for rates, it's going to be B over A, the square root of the ratio of B over A for the molar masses. So the larger something is, the more slowly it's going to move. That's basically it. So I'll give you a list of 4 gases, and you're going to have to pick out which gas is going to move more quickly, which one is going to move more slowly, etc. And just be careful of the idea that some gases are diatomic and some gases are monoatomic. Well, that concludes our review of gas laws. And make sure that you look at the other reviews that I filmed in class. I'll keep them short. And good luck. Okay? Have a good day.